bottom of page 78, we want to look at the second half of section 2.2 about our limits. Today specifically, we're looking at a concept called infinite limits. Now, we talked about this at the end of the year last year as well, but it is possible that sometime when I'm evaluating my limit that I have y values that get infinitely larger without bound. And so the way that we can represent that is we can say that that's going to infinity, and we call that an infinite limit. So let's look at an example of that. Example number 8, they ask us to find the limit of 1 over x squared as x approaches 0. So we would create a table the same way that we always do, where we would go through and say, okay, from the left-hand side, I might use -1, -0.1, -0.01, -0.001. From the right-hand side, 1, 0.1, 0.01, 0.001. And I would go through and I would plug in those values. Now, these are pretty easy to plug in without a calculator. So we could go through and start with -1. If you do -1 squared, does the negative get squared as well? Yes, because it's the whole x value that's being squared, and my x value is -1. So -1 squared would be +1, right? So we would have 1 over 1, which is 1, all right? Then we've got -1/10. If you square a -1/10, what do you get? Yeah, +1/100th. So if I have 1 divided by 1/100th, then I'm just going to get 100, right? And then I've got a -1/100th. So if I square 100th, I get a 10,000th, right? So I'm going to have 1 divided by a 10,000th, which is 10,000. And we could keep going with that process where I look at it and go, okay, I got 3 zeros, or I've got 3 decimal places. So when I square that, I'm going to end up with 6 zeros after my 1. And then divide by that and invert it to multiply by the reciprocal. So you can see that if we're looking for a pattern here, as I go through and add another 0 to my behind the decimal in my x value, it actually generates a couple of zeros added on to the end in my y value. So I can get the idea that if I would come over here and say -0.00001, then I would have a tremendously large number down here, right? So that number is just going to keep getting bigger and bigger and bigger and bigger. And so we would say that that's getting infinitely larger without bound, and we can represent that as infinity. Now, is infinity a number? No. Infinity is not a number. It is a symbol that represents the concept of something getting infinitely larger without bound. We have a hard time understanding that, like wrapping our mind around something getting infinitely larger without bound. Like it literally just kind of makes my brain like, spin in circles like a crazy little spiral kind of thing. Everything in our life has a deadline. We have papers and projects and tests and essays, and we have college applications that are due at a certain time, and we have a graduation date already, and everything in our life, all the way down to death, everything in our life is on a timetable. Everything has an end. So it's really hard for us to imagine something that goes on and on and on without an end. So when I think about infinity, it always reminds me of eternity, because that's the other thing that I think of when I think of something that goes on and on and on without end. And I have just as much trouble wrapping my brain around infinity as I do eternity. Because again, I can't fathom time that never stops, that never ends, without a deadline kind of thing. And so each time I come across the topic of infinity for the first time, as I was looking over this lesson last night and studying it, it just really reminded me of the concept of eternity and thinking about what are the things that really matter. What are the things that I am so stressed out about right now and worried about right now that are causing me so much anxiety? 5 years from now, will they matter? 100 years from now, will it have made any difference? Probably not. So what are the things that really do count? And am I living my life that way? Am I pouring my time and investing myself in the things that are really going to make a difference, and the things that have eternal value? And in particular, spiritually, do you know for sure that if you died today, that you would spend eternity in heaven? What other thing could be more pressing and more important for you to resolve today than that issue, if you don't know that? So again, I would just encourage you, when you think about infinity, to just kind of think about eternity and your priorities and what are the things that really count. So in mathematics, when we have something that gets infinitely larger without bound, we assign it a symbol that represents that concept called infinity. Now, when we say the limit equals infinity, we need to put almost like a little asterisk on that and explain what we're talking about. And they actually do that in the textbook. In the middle of page 79, they give you one of those red Ghostbuster symbols that's like, hey, watch out for this. This is a common mistake that people make. And it says, this does not mean that we are regarding infinity as a number when we say the limit equals infinity. Nor does it mean that the limit actually exists. It simply expresses the particular way in which the limit does not exist. So right here, when I say the limit of 1 over x squared as x approaches 0 from the left equals infinity, I'm not saying that limit exists. What I'm saying is the limit does not exist, and the specific reason why that limit doesn't exist is because it goes to infinity. Now, that's actually a change that AP made a little while back. Before, they used to, on a problem like this, have you give your answer as does not exist. But they changed to ask you to give the answer of infinity, because infinity is actually a better answer than does not exist. A limit doesn't exist for lots of different reasons. We saw some yesterday, like it never settles on one particular value, like it scrolls infinitely at 0, like the trig one that we saw yesterday. Or maybe the limit from the left doesn't equal the limit from the right, so the limit doesn't exist. There are lots of ways a limit doesn't exist. So when I say my limit is infinity, I'm saying my limit doesn't exist, and the reason it doesn't exist is because it goes to infinity. So it's a more precise answer. It'd be like, I think the analogy we used last year was, it would be like if I asked you, do you have a pet? If you said, I have a dog, or you said, I have a golden retriever, those aren't contradictory statements. But saying that you have a golden retriever is a more specific answer. It's saying, I have a dog, and the type of dog I have is a golden retriever. When we give infinity as an answer, we're saying, my limit doesn't exist, and the more specific reason for that is because it goes to infinity. So it's just a better, more specific answer. It does still mean, though, that the limit does not exist. All right, if I were approaching this same function from the right-hand side, and I went through and I plugged in those exact same values, it's just that they're all positive, the y values would be identical, right? Because if you square a negative or you square a positive, you get the same thing. So the exact same thing is going to happen on the limit from the right. Again, those values are going to get infinitely larger without bound, and so we could say that limit is infinity. It honestly doesn't matter if I get, say, positive infinity here and negative infinity here, because the limit already doesn't exist, so it's not like the limit from the left has to equal the limit from the right kind of thing, right? If you look at a graph, the graph would also be another way that we could see that infinite limit. So if I'm approaching 0 from the left-hand side, you can see those y values shoot off to infinity. Or if I'm approaching 0 from the right-hand side, you can see those values shoot off to infinity. What typically makes our graph turn like that? An asymptote, yes. And we learned last year in pre-cal that typically, if you have a denominator that is equal to 0, that causes your function to be undefined at that value, and that generates an asymptote. Now, not always. There are exceptions to that, but that was the way last year that we would identify a vertical asymptote, is we would set the denominator equal to 0. We're going to get a more precise definition for a vertical asymptote today that will help us avoid the pitfalls of what we were working with last year in pre-calc. All right, what if we took that function that we just had, 1 over x squared, and we changed it in just a small way, and we made it 1 over a negative x squared. Now notice that negative is not in the parentheses to be squared. So that means that every one of the answers that I get would be negative, right? So I would build this identical table. It's just that every one of these y values would end up being a negative value. How could I express that limit? It goes to negative infinity, right? And that's the idea of something getting infinitely larger without bound, with each of those values being negative instead of positive. So over on page 79, they give you the definition of the limit that goes to a positive infinity, and on the top of page 80, the definition of a limit that goes to a negative infinity. On the bottom of page 80, they give us a more precise definition of a vertical asymptote than what we have seen previously. They tell me that if you take the limit of a function as x approaches a from either the right or from the left, and you get an answer of either positive or negative infinity, then x equals a will be a vertical asymptote. So yes, I can identify possible vertical asymptotes by setting my denominator equal to 0, but the way that I can prove it or verify it is to use that actual definition and to show that the limit as I approached that numerical value from either the left or from the right went to infinity or negative infinity. And we'll come back to that in just a minute in another example. All right, look at example number 9. For example number 9, we have the limit as x approaches 3 from the right and from the left for 2 over x minus 3. We are going to do this type of limit a million times between now and May. And if every time I have to do it, I have to pull out a calculator and create a table of values, I am going to make myself most miserable. And on the AP exam, these type of questions will be on the part of the exam without a calculator. I'll be expected to be able to evaluate this type of a limit without a calculator. So I've made you a little note out there in the margin that for something like example 9, I want to do this without a calculator. Okay, how in the world do I do that without a calculator? All right, let's talk through it and talk about the logic that we'll be able to use to evaluate this. If I were looking for the limit where I'm approaching 3 from the right, I would use values like 3.1, 3.01, 3.001, right? Okay, so my numerator is staying the same. It's not changing. In my denominator, I'm putting in 3.1. So 3.1 minus 3 is 0.1, right? Then I put in 3.01. So 3.01 minus 3 is 0.01. 3.001 minus 3 is 0.001. So that denominator is getting smaller and smaller and smaller, right? It was 0.1, 0.01, 0.001. So if my numerator is staying the same and my denominator is getting smaller and smaller and smaller, what will the overall fraction be doing? Getting larger and larger and larger, right? Let's talk through that one more time. My numerator is staying the same. It is not changing. It's 2 no matter what I plug in. But for my denominator, as I approach 3 from the right, I would use like 3.1, 3.01, 3.001. So for each of those, when I subtract 3, I would be left with 0.1, then 0.01, then 0.001. So that denominator is getting smaller and smaller and smaller. So if my numerator is staying the same and my denominator gets smaller and smaller and smaller, the overall fraction is going to get bigger and bigger and bigger. And so it's going to get larger and larger without bound. And so I could say that that limit is infinity. Because it was a positive 2 divided by every one of these guys down here ended up being a positive value, a positive divided by a positive is going to yield a positive infinity. All right, but look at this one. If I'm approaching 3 from the left-hand side, the numerator is still staying the same, not changing. But my denominator, I would be using values like 2.9, and then 2.99, and then 2.999, right? So if I do 2.9 minus 3, that's going to be a negative 0.1. And if I do 2.99 minus 3, that'd be a negative 0.01. 2.999 minus 3, negative 0.001. So again, my numerator is staying the same and my denominator is getting smaller and smaller, 0.1, 0.01, 0.001. So the overall fraction will still be getting infinitely larger without bound. But because this was a positive divided by a negative, then I would get a negative infinity for that limit. So when you're doing the homework tonight, practice on those types of problems, doing them without a calculator, thinking through that logic process so we begin to get comfortable with that and so that we can use that on a regular basis. Now, because I took the limit as x approaches 3 from the right and got infinity, what does that mean about 3? In the graph, right, that value does not exist. What would show up on the graph at that point then? A vertical asymptote, yes. So by the definition that they gave me on page 80, because the limit as x approached 3 from the right gave me infinity, then x equals 3 has to be a vertical asymptote. I also could have used this other piece, that because I approached 3 from the left and got negative infinity, that also would have meant that x equals 3 is a vertical asymptote. Either one of those, I don't need both, just one or the other. So what happens on the AP exam is half of the AP exam is FRQs, free response questions, where they'll ask me to work out problems just like we do on our test, where we'll work them out and we'll come to an answer. But a lot of times on those free response questions, it will say find the answer, and then it will say justify or prove your answer. When they're saying justify or prove your answer, it's not enough to just come up with x equals 3 as a vertical asymptote. They then want to know what gives you the right to make that assumption. And the only thing that you can use is a definition or a theorem or a postulate or a rule or something from calculus. So the justification for this would be the definition. If I had to justify this, I would just say x equals 3 is a vertical asymptote because the limit as x approaches 3 from the right for that function was positive infinity. I would have to give proof of my answer. So let's look at another one of those and look at, of course, there's the graph that would back up what we found algebraically. But let's look at another one of those and look at the justification that we would need for AP. All right, for example number 10, it says find the vertical asymptotes for tangent. All right, so I know what the tangent curve looks like. At least I should know what the tangent curve looks like. We studied that in our appendices not too long ago, so I should be able to generate that by hand without my calculator. So looking at that graph, I know that there are vertical asymptotes at the multiples of pi over 2. At pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. So a concise way of saying that is pi over 2 plus the multiples of pi over 2. When we say the multiples of pi over 2, because tangent has a period of 1 pi, the exact same thing is going to happen every pi, right? So I would want to say take pi over 2 and add the multiples of pi to it. So n could be 0, 1, 2, 3, negative 1, negative 2, negative 3. I just need to specify then negative 3, negative 2, negative 1, 0, 1, 2, 3. Those are integers, right? Positive and negative whole numbers. So I would just need to specify that n has to be an integer. If then I was told that I had to justify my answer, if I only had to justify one of them, like let's say I was only trying to justify that x equals pi over 2 is a vertical asymptote, then here's what I could state. All I would need to do is show that the limit approaching that a value went to either infinity or negative infinity. I don't have to state both. So I can either show that as I approach pi over 2 from the left-hand side it goes to infinity, or as I approach it from the right-hand side it goes to negative infinity. Either one of those. So all I would state is that the limit approaching pi over 2 went to infinity or negative infinity, whichever one you used from the left or from the right. Therefore, x equals pi over 2 is a vertical asymptote. That's the justification they would be looking for on the AP exam. If they ask me to justify not just one vertical asymptote, but all of them, then I'm going to pull in that idea of a coterminal and a period. So I could go through and I could say, okay, because tangent is periodic and its period is 1 pi, then if you add pi over n, where again we've already stated n is an integer, if we add pi over n, every one of those would be vertical asymptotes as well. So again, I can't just state that. I have to give a reason behind that idea of what the period of tangent is and that it would repeat itself at each of those places. Okay? So we want to start kind of getting that in mind, as this is the first section that we've come into where we actually are doing calculus. From this point forward, we want to think about not only the answer that we're coming up with, but how we could prove our answer or how we could justify it if we were asked to do so. Okay? So here is our homework for tonight. On pages 82 to 83, we're doing 8, 9, 13, 21, 25, 27, 29. And then I've said challenge any. That just means that you can choose any problem that we haven't already done from this section as your challenge. So you know what you need extra practice with. You could choose the thing that you would like a little additional practice with for your challenge.